So today's lesson is going to be the first in our Algebra 2 unit, and we're just going to focus on the idea of Nags, or N-A-G-S, and that acronym represents the numerous ways that we can represent numerical data in a function. So the N is going to stand for numerical, the A stands for algebraic, the G stands for graphical, and the S stands for sentence. So we're going to be looking at ways that we can interpret data in these four different modalities. You're more than welcome to use multiple colors, to add any notes that you feel like are significant to your notebook, but I'm just going to give you kind of the brief summary of what we're doing here. So if you flip your tab open from the middle, what you're going to have are these interior squares that we're going to take our notes on. So it's almost like flipping up a little folder, a little window, and now we're going to take our notes inside the foldable. So when we talk about numerical representations of graphs, what we're really talking about are the ordered pairs. And if you remember anything about a coordinate plane from Algebra 1, you know that there are coordinate pairs that get placed on a particular xy axis. And when we write ordered pairs, they get written in the order x, comma, y. And then they're placed along the graph. So if we have a set of ordered pairs, those pairs will be placed in larger brackets, and there will be several pairs. So we might have 0, 2, 2, 4, and so on. We'll have several ordered pairs within that data set. Another way that we can numerically write data is within an input-output table. So input, output. And just thinking about the way that those words are used, input is the number that goes into the function. Output is the number that comes out of the function, right? So the input is going to be our x value, and the output is going to be our y. So this is just another way for us to write our ordered pairs in table form, really. Some people prefer this when they're graphing. It's up to you personally whether you want to have a table or just specific coordinate pairs that you're working with. When we look at writing information about a function graphically, again, we're looking at a coordinate plane with coordinate pairs, right? So you're often going to see an x and y axis with coordinate points graphed throughout the plane. In addition, you might also see an input-output table, but it's a little different. It's called a mapping diagram. And the key difference between an input-output table and a mapping diagram is that in an input-output table, every specific coordinate point gets its own row of the table, right? So we had two coordinate points that were our examples, 0, 2, and then 2, 4. Each of those get their own rows within the table. In a mapping diagram, you may have, for example, two coordinate points that lie on the same x-axis. So if you can see, I just plotted these 2 points along this line of x, which means when I graphed them, they would have the same x value. Let's say that x value is 2. So let's call this first point here 2, -1, and then the second point 2, -3. Those coordinates would go on separate lines, but there would only be one need for the x coordinate specifically. So even though my coordinate point 2, -1 and 2, -3 are two distinct points, because the input value is the same, I don't need to repeat it. if that makes sense. So specifically, you can have more output values than you do input values in a mapping diagram. Also, when you're creating a mapping diagram, both the input and the output values in your table are going to go in numerical order. And then you draw your arrows to connect the input values to the appropriate output values. So we'll do a few more examples of that in class, but I just wanted to touch base on the differences between an input-output table and a mapping diagram. Moving on to the algebraic section in your notes, again, flip open that tab so that you can write on the inside. When we talk about things that are algebraic, we're looking at actual functions or ways to write functions, right? So even though we may not be using variables yet, we're still thinking about what numbers can be represented by and how we can phrase those in numerical expressions. So for example, if I knew that milk was $4 a gallon, and I wanted to know how much the total price of milk would be, I can write out an algebraic expression because $4 per gallon would mean $4 times 1 gallon would be the cost of 1 gallon of milk, $4 times 2 would be the cost of 2 gallons of milk, right? Equals the total price of the milk. So I can write it just like this. I can write it in more elaborate words. $4 per gallon of milk equals the total price of milk. I can just write it as a very specific function for G equals T. Right? These are all algebraic expressions. Another example, if I have a certain number of pieces of candy, so if I have pieces of candy in a bag, and I want to know how much candy each person will get if there's 15 people, I want to divide that candy evenly into 15, and then I'm going to know how many pieces of candy each person gets. So I can write that just with variables, or I can write it a little more elaborated. Sometimes people like to write out the pieces divided by 15 equals pieces per person. Especially when you're first writing your own algebraic expressions, it might help you to create more descriptions with your words. I would say whenever you do this, just make sure that one specific component of your equation is in parentheses. So if I don't feel like instead of having the total number of pieces divided by 15 equals the number of pieces for each person, I feel like it's equals the number of pieces times the number of people, right? You want to make sure that you're very clear as to which parts of that equation are single variables. The last representation that we'll look at is sentences, and this should be pretty straightforward. We're just thinking about how sentences represent equations. So if I was going to say 2 candy bars cost $1, and 3 candy bars cost $1.50. This particular sentence actually represents a function, right? It's telling me how much the candy costs individually. So if 2 costs $1 and 3 costs $1.50, I could do myself a favor and put an input-output table and say 2 candy bars is $1, 3 candy bars is $1.50. I could write myself an equation. So I could say for every 2 candy bars, I equal $1, or I could say if 2 candy bars equals $1, how much is 1 candy bar equal? And then I could find the cost of any number of candy bars from there. Sentence form is really the most basic, and we're not going to see a lot of it in real formal algebra proofs, but in this case, I figured I'd give you that little hint. So what we'll be working on moving forward in class is being able to take the same information and represent it numerically, algebraically, graphically, and in sentence form. So you'll get a few questions next class to look at and represent in those 4 ways. So be sure that you can tell the difference between each of those representations and also clarify some of those nuances, like the things between the input-output table and the mapping diagram. and also the difference between algebraic and sentence forms.